Last time we just talked about the system's differential equation, and the solution for the homogeneous equation, system equations, will be omega times c. Okay, and here's omega and the constant. Now, this omega is called fundamental matrix. Now, if I have a non-homogeneous system, now what is the solution? We can see that in a single equation, we can just compare that to the single equation. For the single equation, the general solution will be the homogeneous solution plus the particular solution, right? Then here we can apply the same idea to the non-homogeneous system equation. If I have a non-homogeneous system, then I also have a general solution, the homogeneous solution, plus the particular solution. So here is our particular solution. And how do we find the non-homogeneous system equation? We'll see either today or next week, well, or on Wednesday. So just remember that for the non-homogeneous system, we also have a particular solution, and we will talk about that later. Then back to our homogeneous linear system with a constant coefficient. For the constant coefficients, here the A is a constant matrix. So we don't know how do we find the solution, but at least we can go through what we have already learned. For the single equation, x prime equals ax, then we guess and we know the solution is the constant times e to the at, because x prime will be c a e to the at equals a c e to the at. So they can also cancel out, they are equal. Okay, so that is our solution. But how about x is not just a single equation? We consider two equations or even more. It becomes a linear system. So now the vector x, for the vector x, then the solution should be similar. So we have c e to the lambda t. And we can guess this solution is like in this form. So we can bring this solution back to our equation. If we bring this, substitute into equation, x prime equals ax, then you'll get x c, this is a vector, no, lambda c e to the lambda t equals right hand side ax c e to the a is a matrix, c is a vector, e to the lambda t. Then you get a c equals lambda c, and a minus lambda I c equals 0 vector. So it looks like the c and the lambda is the eigenvalue, c is the eigenvector of matrix A. That is the solution. So in this case, with a non-trivial solution, lambda is not equal to 0. Otherwise, you can see that we can say that lambda equals 0. They always satisfy that. But if lambda is, no, if the c is not 0, this term is not 0, then the determinant of this matrix should be 0. Then that's why lambda is the eigenvalue of matrix A. Lambda eigenvalues of matrix A. And we also call this is the characteristic values. And like C is the eigenvector. Eigenvectors of matrix A. And for this determinant, we have A11 minus lambda A21 to AN1. Here A12 to A1N M. Here's A22 minus lambda to A2M AN2. And here this is AMM minus lambda. This determinant should be 0. And to calculate this determinant using the decomposition, but finally you will see that I will have the nth term for the lambda. The power of lambda will be n. Then you'll get lambda to the n is a lambda polynomial plus the coefficient, say alpha n minus 1 lambda n minus 1 to alpha 1 lambda plus alpha not equals 0. This is called characteristic equation for lambda. So since this is n polynomial, I expect I have n roots for lambda for lambda. So n roots like lambda 1, lambda 2 to lambda n. For those lambdas, the eigenvalues, it could be complex number or repeated, maybe complex conjugate. Or repeated. and their corresponding eigenvectors are cos1, cos2, 2 cosn. And for those eigenvectors, they are not necessarily linearly independent. So this combination, well, the cos times the exponential cos1, cos2, 2 cos n. For these n terms, for those n terms, they are all solutions. Are all solutions to this system's differential equation, homogeneous system's differential equation with constant coefficient. X prime equals a x. So now let's see a theory. A is an n by n constant matrix, and A has linearly independent eigenvectors. Then those are linearly independent solutions. We also call the fundamental solutions, and we can write it down. The general solution will be the linear combination of this combination. Well, linear combinations of your eigenvalues and eigenvectors. Okay. See the difference here. All right. If you can find the linear independent eigenvectors, then the combination of those eigenvectors with the eigenvalues, this is the general solution. And for each term, this will be formed as fundamental solutions. For example, for 2 by 2 matrix, the eigenvalues are either 1 or 6. When the eigenvalue is 1, the eigenvector cos is 1 minus 3 over 2. When eigenvalue is 6, then the eigenvector is 1, 1. You can see those two eigenvectors are distinct. So they are linearly independent. Since they are linearly independent, I can write the general solution of this system. So the general solution of this system x constant and the eigenvector 1 minus 3 over 2 times e to the lambda t. Lambda is 1, so t. Second one, e to the lambda 6t. So your general solution is, we can have a fundamental matrix e to the t minus 3 over 2 e to the 6 t e to the 6t e to the 6t. C1, C2. And this is your fundamental matrix, omega. You can also write down the components of the system solution, the general solution. So components of the general solution. X1. X1 is here. Okay, this is X1 and this is X2. C1 e to the t plus C2 e to the 6t. And X2 is minus 3 over 2 e to the t C1 plus C2 e to the 6t. Now that is just 2 by 2 matrix for A. Now let's see another one that's 3 by 3. Then to find the solution, we also need to find the eigenvalues and the eigenvectors. So let me give you 5 minutes. Try to find the eigenvalues and the eigenvectors for matrix A. Because no matter what, every time you need to find the eigenvalues and eigenvectors. Right? You can check if this matrix is orthogonal matrix or orthonormal matrix or whatever. That you need to find the eigenvalues and the eigenvectors. So if you don't know how to find the eigenvalues and eigenvectors, you probably will be failed in the exam, because almost every question we need to ask you to find the eigenvalues and eigenvectors. That is the basic requirement, and then using the eigenvalues and eigenvectors to do something else. So anyone for eigenvalues? Yes. 1 and minus 1. 1 is correct. We have 1. Since it is 3 by 3, right? We expect to get 3 eigenvalues. And for the eigenvalue 1, the eigenvector is 1, 0, 0. Again, how about the rest two? First, we can check the eigenvalue 1. Okay, so A minus lambda 1 I. To find the eigenvector, because C1, we have 0, 0, 0, 0, 0, 2, 1, 1, 0. Times eigenvector, because C1, it could be because C1, 1, because C2, 1, because C3, 1. This is C1 vector. That should be equal to a 0 vector. In this case, the first row we have c3 1 equals 0. The second row c2 1 equals 0. And the third row 2 c2 1 equals 0. Then we get c2 1 0. c3 1 0. Okay. So I can choose c1. The second one and third one should be 0. And the first one, whatever you want. And for simplicity, I choose 1. Okay, so you may also choose the first element as square root of 2, minus 100 or pi, whatever, as long as it is not 0. So you can choose like square root of 2, 0, 0, or minus 100, 0, 0, or even you like pi, 0, 0. Those are fine. Okay, so the second and third eigenvalues are 1 plus square root of 2 with the associated eigenvectors 1, 1 square root of 2. 1 minus square root of 2. Then we have 1, 1 minus square root of 2. Okay, so now I have 3 eigenvalues and their associated eigenvectors. I can write the general solution for this for this homogeneous linear systems with constant matrix, constant coefficients. The general solution is the x c1 eigenvalue 1, eigenvector times e to the eigenvalue 1t, c2 eigenvector 2, e to the eigenvalue 2t, c3 the linear combination. Okay, here is eigenvector 3, e to the eigenvalue 3t. So c1 1, 0, 0, e to the t. c2 1, 1 square root of 2, e to the 1 plus square root of 2t. c3 1, 1 minus square root of 2, e to the 1 minus square root of 2t. To get the fundamental matrix e to the t 0, 0, e to the 1 plus square root of t, e to the 1 plus square root of 2 times t, square root of 2 times e to the 1 plus square root of 2 times t. Similarly, here's 1 minus square root of t. Okay, so this is our fundamental matrix. So far, did you observe anything from the fundamental matrix? Any questions for this one? If not, for the next one, A is here. And then we still need to find the eigenvalues and the eigenvectors. This time, I give you the eigenvalues. So try to find the eigenvectors. Suppose you know the eigenvalues are 1, and -3. So please find the 3 eigenvectors. So you can also try to find this first. When eigenvalue is -3, what is their associated eigenvector? You can also see that now I have a repeated eigenvalues. So for the repeated eigenvalues, how do we find the eigenvectors? So if we really see the matrix, you can see that all these 3 rows are linearly dependent. But we still need to make this equals to 0, like x minus x1 minus x2 plus x3 equals 0, right? So we can either choose like 1, 1, 0, 1, 0, minus 1, or minus 1, 1, minus 1, 0, 1. They all satisfy this equation. So we can choose the first eigenvectors 1, 1, 0, and second eigenvectors, the second eigenvector minus 1, 0, 1. And for this eigenvalues -3, the associated eigenvector is 1, 3, 1. So now I have 3 eigenvalues and 3 eigenvectors. My general solution xt is C1 1, 1, 0 e to the t plus C2 minus 1, 0, 1 e to the t, and C3 1, 3, 1 e to the minus 3t. Any questions for this example? Now, if you don't have any questions, then the next one. Still a matrix A. I want to find the eigenvalues and the eigenvectors. So this time the eigenvalues are 2. The first is 2, and their associated eigenvector 1, 0, 0. The second eigenvalue is -1 plus square root of 3i. Then the associated eigenvector 1 minus 2 square root of 3i minus 3 plus square root of 3i. Then the last one, eigenvalue is, since you see the complex number, for the eigenvalues, we should have conjugate of these eigenvalues. So -1 minus square root of 3. And their associated eigenvector, also do the conjugate. You can see this conjugate. And then you can write it down, the general solution. The general solution C1 eigenvector 1 times e to the 2t C2 eigenvector 2 and then exponential e to the minus 1 plus square root of 3 I t and C3 1 2 square root of 3 minus 3 plus square root of 3i e to the minus 1 minus square root of 3i t. Okay, and now you can see that I have a constant matrix, and then I want to find the solution of the differential equation. But they give us the solution with complex number inside, which is not straightforward. So I want to see the solution in just the real form. To see this in the real form, well, we need to manipulate a little bit, just what we learned for the single equation. So we need to use the Euler formula. First, to get the solution in real form, we consider the eigenvector 2, while the second solution e to the lambda 2t times the eigenvector 2, that's 1 0 minus 3 plus I 0 minus 2 square root of 3 square root of 3 e to the minus t times cosine, using the Euler formula, cosine square root of 3t plus I sine square root of 3t. Similarly, for the third eigenvector, doing the same thing. E to the minus t, here cosine square root of 3t minus I sine square root of 3t. So now this is a complex form. Okay, I have a complex number here. I want to express the solution in the real form. So remember that if x1 is a solution, x2 is a solution, then the linear combination of x1 plus x2 is also a solution. Right? It could be plus 3x2 or even minus 4x2 or 2x1 plus 4x2. They are also solutions. So in this concept, these two solutions summed together will be also a solution. That means we have 1, 0, minus 3. If I add this together, they will cancel the complex term, the imaginary part. Cosine square root of 3t minus 0 minus 2 times square root of 3 sine square root of 3t. Okay, this is solution. No imaginary, no complex numbers here. And if I subtract these two solution, divide by I, this is also a solution. So this will be 2i divided by I e to the minus t 1, 0, minus 3 sine square root of 3t plus 0 minus 2 square root of 3 square root of 3 cosine square root of 3t. So the general solution in real form is x equals c1 e to the 2t 1, 0, 0 and linear combination for c2 103 cosine square root of 3t and one more for c3. Okay, so now in general, if the matrix A has the complex conjugate eigenvalues and the eigenvectors, if A with complex conjugate eigenvalues and eigenvectors, eigenvalues and eigenvectors. Maybe I also change eigenvalues as blue. And the eigenvalues are alpha plus I beta and alpha plus minus I beta. And the vector u plus iv and also u minus iv. Then I can have two linear independent solutions in real form. The two linear independent solutions in real form are e to the alpha t u cosine beta t minus v vector sine beta t. And the other one, e to the alpha t u sine beta t plus v cosine beta t. Okay, so now to find the solution x prime equals ax, we know that, I can find the eigenvalues and eigenvectors of the matrix A, and then the solution will be eigenvector times e to the eigenvalue t, and you do the linear combination. Okay, next page. But don't you think that if we do the single equation x prime equals ax, then we guess the solution is c times the e to the at. Now a is here, right? If I make it to a system, then my solution could be e to the at times k. Then what is e to the at? The exponential matrix. How do we find the exponential matrix? If we know the expansion e to the at here, then we can also think about e to the at, the matrix A will be identity matrix plus at plus 1 over 2 factorial a squared t squared, and also 1 over 3 factorial a cube t cube, and so on. And then a here, a squared is a times a. Okay. And the following is one way to find the exponential matrix, and I think that's too difficult. So we will introduce 3 other ways to find the exponential matrix next week. So for this part, we skip first. Okay, if we have time, then we can come back to talk about the generalized eigenvectors. But now just having something in mind that seems for the single equation, we have x equals 8x, then the solution should be e to the at. For the system equation, we also have e to the at, then this a is a matrix. And how do we find the exponential matrix? We will see it, definitely not today. Okay. So now before we just find the exponential matrix form, let's see how do we find the solution for the non-homogeneous. We have this part, this G vector here. To find the solution of the non-homogeneous systems, we have 2 methods. The first one is called the diagonalization method, and the second one is called the method of variation of parameters. Okay, this term should be familiar, right? We learned this in the first topic. But before that, let's just talk about how do we use the diagonalization method to find a non-homogeneous solution. To find the solution of a non-homogeneous system. So first, the diagonal method. We say A is a constant diagonalizable matrix then it exists a non-singular matrix P. Then P inverse AP is a diagonal matrix. A non-singular matrix, what does that mean, a non-singular matrix? When you see that it is a non-singular matrix, that means the determinant of this matrix P is what? Equal to 0 or not equal to 0? If it is non-singular, it should be not equal to 0. Okay, so here is the theory. A n by n matrix, and it has n linear independent eigenvectors, C1 to Cn, with these associated eigenvalues lambda 1 to lambda n. Then P inverse AP will be a diagonal matrix, and here's a diagonal matrix. And you can see that the offline, oh no, not offline. Well, yeah, the offline diagonal will be all zeros, and then the diagonal elements are eigenvalues. And for those eigenvalues, actually, it could be distinct, but may not be distinct. Maybe some of the eigenvalues are the same, but they have different eigenvectors, right? That is what we just practiced, the example. We have eigenvalues 1, 2 repeated eigenvalues, but we have different eigenvectors. And for the P, this matrix P is formed by the eigenvectors. So here you can see those are the eigenvectors. Then what is the diagonalization method? It's try to change the variables and decouple the system. So here, for this system, you can see that I have a cross term, x1, x2 together, because, for example, x1, x2 equals 3, 1, 2, 4, x1, x2 plus something. Okay. In this way, x1 prime will be 3x1 plus 2x2 plus something. I have x1 and x2 together. But now, using the diagonalization method, I can decouple this system, which means that I can express x1, a differential equation, and x2 differential equation separately. Okay, so now let's see how do we see this result. P diagonalizes A. Then we can define another vector z. The z is P inverse x, because just changing variables, x, now x becomes P z. Okay, so you change all x to pz. So the original differential equation, non-homogeneous, x prime equals a x plus g becomes p z prime equals a x becomes pz plus g. P is a matrix, so P same, but Z becomes Z prime equals A P Z G. So we get Z prime equals, to get Z prime, how do I get the Z prime? Times P inverse. So here I have a P inverse. Okay. So I get P inverse A P Z plus P inverse G. And for this term, this is a diagonal matrix D lambda. So now let's see this equation. Z prom. Z is Z1 prom, Z2 prom to Zn prom. And the diagonal matrix D, we have lambda 1, lambda 2, 2, lambda n. And the off diagonals will be O0, Z1, Z2, 2, Zn. This equal to, well, P inverse G, let's say it's F, F1, F2 to Fn. So we can say that the P inverse G is the function F1t, F2t till Fnt. So now you can see how I decoupled the system. You have Z1. Z1 prom equals lambda 1 Z1 plus F1. Z2 prom equals lambda 2 Z2 plus F2. And then you continue, get Zn prom equals lambda n Zn plus Fnt. Well, that's why I say that for the finals, you still need to use some knowledges like in topic 1. Okay, how do you find this equation, the single equation? Decouple system. Here's a note. Decouple the system can solve each differential equation separately and independently. Okay. And I think that you need to use this diagonalization method to find the solution in your final. Any questions so far for this derivation? Then now we can use a real question to find the solution. Here I have two equations that forms a system x1 and x2. So if I write it down in the matrix form, x1 prom, x2 prom, 3, 1, 3, 5, x1, x2 plus 8, 4 times e to 3t. Okay, this is the matrix form. And here we have A, and this is a G. Again, that this is non-homogeneous system. So to use the diagonalization method, we still need to find the eigenvalue, eigenvector first of this matrix A. So the eigenvector, the eigenvalue are the first eigenvalue is 2. Then the eigenvector is -3, 1. The second eigenvector, the eigenvalue is 6. Then the associated eigenvector 1, 1. So since we have eigenvectors, I can form the matrix P. And the P is -3, 1, 1, 1. Then you can find the P inverse. You see another one, you need to know how to find the inverse. Okay. The inverse will be 1 minus 1 over 4, 1 over 4, 1 over 4, and 3 over 4. And then once you have a P and P inverse, then changing variables, we can get the Z. The Z vector Z1, Z1, Z2 is the P inverse times X. Then you get -1/4 X1 plus 1/4 X2. And 1 over 4 X1 plus 3 over 4 X2. So you get Z1 prime, Z2 prime equals, you do P inverse AP, right? Do you really need to do this multiplication? No, because we know this is diagonal matrix and the elements are the eigenvalues. Okay, so here, this is a diagonal matrix. This matrix, the first element should be 2. And second one, 6. Z1, Z2. And then P inverse G. P inverse G that you need to calculate. So this you can see Z1 prime equals 2Z1 minus 2 plus e to the 3t. There's no Z2. You can find Z1 directly, and Z2 prime equals 6 Z2 plus 2 plus 3 e to the 3t. Then you can get C1 e to the 2t plus 1 plus e to the 3t. And C2 e to the 6t minus 1/3 plus e to the 3t. You can see that I have a coefficients here, C1, C2. That is the homogeneous. See this? We need to do homogeneous one, and then later on add this particular forcing function. So here, this is your particular solution. You don't need to find it again. In the past, we need to find a general solution, and then we guess the form of the particular solution and bring that guess to the original equation again to find your particular solution. But in this way, we can find the general solution and particular solution all together. And then the next step is that convert it to x, because I want to see the result, the answer of x. So we convert to x. And what is x? P, z. So we have a p and we also have a z. Then you can rearrange that to get your fundamental matrix times your constant c. Then you get here I have my particular solution minus 4 e to the 3t minus 10 over 3, and here's 2 over 3. Okay, so here this is my fundamental matrix omega, and this is the constant c, and then here is the particular solution. Write it down again. Then how do I determine the constant c? If I have a initial condition, so if I have the initial condition like 5 over 3 or 11 over 3, then I can get the C1, C2 as here. Any questions for this method? Now, if you don't have any questions, the next method is called the method of variation of parameters. Remember that for this non-homogeneous equations, the homogeneous solution, suppose it is e to the at. Then to find the particular solution, we let particular solution is the homogeneous solution times another function t. In that case, bring this back to the original non-homogeneous equation. We have xp prom. If I take a prom, then using the chain rules, we have two terms. For these two terms, this should be equal to the right hand side. Okay, right hand side here. Then we can get the u prom, because the u prom is e to the minus at times the function of g, and then your u, you can take the integration e to the minus at gt dt. So the particular solution is ut, the function of u times the homogeneous solution e to the at. That becomes e to the at integration and overall the general solution x will be c e to the at, that's the homogeneous solution, plus the particular solution. That is for the single equation. Then similarly, we follow this concept to consider the system equation. Follow this concept, that means for the solution of this non-homogeneous equation, then we have the solution has the form x equals the fundamental matrix times the constant and then the phi. Then for this particular solution will be the homogeneous solution times a function u as well. So the fundamental matrix times u. Then when you take the derivative of the phi, you have omega prom u using the chain rule. So for this chain rule, we can get omega times u prom this should be equal to gt. So your u prom will be the inverse of the fundamental matrix times G. Then you can find your particular solution phi. Okay. And then we will do one example. So on Wednesday, we will talk about 3 methods to find the exponential matrix. Okay, so now let's see this example. Again, that we need to find the eigenvalues and eigenvectors. So first eigenvalue is -1. Their associated eigenvector is 5, 1. The second eigenvalue is 6. Then the eigenvector is -2, 1. So in that case, the fundamental matrix will be 5 times e to the minus t minus 2 times e to the 6t e to the minus t e to the 6t. And you need to know how do you find the inverse matrix. And then you can have the inverse of the fundamental matrix times G. You get 1/7. Once you get this term, then you can find the u function. Here the u function, you need to take the integration. Which means you need to take two integrations. The first is in the first row. So in that case, the general solution is X with the homogeneous solution plus the particular solution. And if you have initial conditions, then you can determine this coefficient C1 and C2. Any questions for this? We are going to talk about the exponential matrix form. How do we find the exponential matrix e to the at? Okay, and as I said, that we have three methods, and the first one we are going to learn is called diagonalization method. So what is diagonalization method? Suppose we know that A can be expressed as P D P inverse. The D is a diagonal matrix. Okay, and then that also means D can be expressed as P inverse AP. Okay, and when I have D to the N, then for the right hand side, I only have to get A to the N, and we put the P. We just put the P and P inverse. Okay, so in this case, we can also predict the A to the N, and product the matrix A n times. A to the N. Then what is A? P D P inverse, right? And then another A, P D P inverse, and another A, because we need n times. So here's P inverse. Okay, so overall we have n times of P dP inverse. And you can see P inverse times P inverse product P, they'll cancel out because they are identity matrix. So finally, you will get P d to the n P inverse. Right? And we know that D is a diagonal matrix. So if it is a diagonal matrix, D is a diagonal matrix, say lambda 1, lambda 2, and others are 0, then D square, I only need to square the diagonal elements. D cube. Okay, so D to the n, that is P. Here I have lambda 1 to the n, lambda 2 to the n, till lambda n to the n. And P inverse. Okay, with this concept, let's see e to the at. That is identity matrix plus we take the Taylor expansion. Then I have 1 over 2 factorial a square t square and 1 over 3 factorial a cube t cube and so on. Now, what is A? A is P dP inverse. So let's just change the expression of A to P dP inverse times T plus 1 over 2 factorial P d square P inverse T square and 1 over 3 factorial P d cube P inverse T square, T cube. Then next step, we put P outside. I have I identity matrix dt 1 over 2 factorial d square t square and P inverse. Because overall P I identity matrix P inverse is still identity matrix. So this gives you P e to the t d t P inverse. So what is e to the d t? Here e to the lambda 1 t, e to the lambda 2 t, to e to the lambda n t, and the off diagonal elements are all zeros. Okay, so again, to find the exponential matrix form, Well, we still need to find the eigenvalues, and also P is formed by eigenvectors. Okay? So let's do this example. This is A, and I want to find e to the AT. First, I need to find the eigenvalues and their associated eigenvectors. Once you found the eigenvalues and eigenvectors, then you have done probably 90%. So for this A matrix, my eigenvalues first is I, and their associated eigenvector is 1I. And the second eigenvalue is minus I. If you found I, then the other one, definitely the conjugate, minus I. And then the eigenvector, also conjugated, 1 minus I. Then you can form the matrix P. 1I, 1 minus I. And also you know your diagonal matrix, because the diagonal matrix is formed by your eigenvalue, I, 0, 0, minus I. Remember, this should be to some degree related. Okay, if you put 1I in the first column, then your first column of your diagonal matrix should be the corresponding eigenvalue. Okay, if you switch, say 1 minus I, 1I, then your diagonal matrix should be minus I, 0, 0I. Right? And once we have the eigenvalues and the matrix that can diagonalize the matrix A, which is P, then we can find the exponential matrix form e to the AT. That's P e to the DT, P inverse. So you need to know how to find the P, and once you find the matrix P, then you know how to write your diagonal matrix D. And here there will be IT, e to the minus IT. The next step is that since you have the matrix P, then you need to know how do you find the inverse of that matrix P. Well, the first two matrix, we have its product here. Okay, now let's review how do we find the inverse. The determinant. And then since it is 2 by 2, so just switch. Or you can see that here, and for this part, 1. Minus I, 1. To have this part, right? To have this part, then we need to go to the diagonal, the symmetric one. So this is 1. And minus I. So we have cosine t minus sine t, sine t, cosine t. It's a rotation matrix. Okay? 3 methods. The first one is called diagonalization method. And the second one, we will talk about that later. The third one is called just use the Laplace transform to find the exponential matrix. Okay, so again, that you need to use the Laplace transform. Let's review. First, if I have e to the at, this scalar a, then that means this is the inverse Laplace transform of s minus a, right? Then we can use this concept similarly to apply a now becomes a matrix. It should be, since it is a matrix, my s should be times the identity matrix minus a and you can either write it down as identity matrix minus a matrix and the inverse. So for this example, as identity matrix minus a, that is as identity matrix and minus the a matrix 1, 2, minus 1, minus 2. So we have s minus 1, minus 2, 1, s plus 2. So the inverse is okay, here's the inverse. Then we will check the table. Okay, normally we just check the table first. If this form can satisfy the table, that the Laplace transform pairs, then we don't need to really calculate the inverse. Okay, so in this case, I know the inverse of this, inverse this, inverse of this. So e to the at will be the inverse Laplace transform of the identity matrix times s minus a inverse. So when you check the table, 2 over s will be 2 minus e to the minus t. 2 minus e to the 2 times e minus t. And e, here e minus e to the minus t minus 1. Minus 1 plus 2 times e to the minus t. Why it works? Here's the reason. First, e to the x, the Taylor series expansion or Taylor expansion, that's 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, and so on. So it should be 1 over n factorial x to the n. So e to the at with the matrix A. It should be identity matrix plus A matrix times T, and the next term 1 over 2 factorial A square T square, 1 over 3 factorial A cube T cube. And also 1 over n factorial A to the n T to the n. So when we take the Laplace transform e to the a t, there'll be I Laplace transform of 1 plus a Laplace transform of t, 1 over 2 factorial a square Laplace transform of t square, and so on. Here should be 1 over n factorial a to the n Laplace transform of t to the n. So Laplace transform of 1 is 1 over s. Laplace transform of t is 1 over s squared. And so on. Then we can take the 1 over s outside. Then I have identity matrix plus 1 over s a plus 1 over s square a square plus 1 over s to the n a to the n. So here is 1 over s and for this part, that is identity matrix minus 1 over s a matrix is a series, infinite series, and it can converge. So that's why it is as identity matrix minus a. Okay. If you don't have any questions, let's see this. The last method is called Jordan canonical form. First, I need you to help me find the eigenvalues and eigenvectors for this matrix. Shouldn't be that difficult. Okay, what are the eigenvalues and also their associated eigenvectors? So now I have my eigenvalues lambda 1 equals lambda 2 equals lambda 3, that is 2. And then for these three eigenvalues, I can only find one eigenvector, that is 1, 0, 0, right? And that's it. I cannot find the other two. Okay, but remember that if I want to find a matrix that diagonalizes A, I need to form the matrix P, and that means I need two more eigenvectors. But so far I only have one eigenvector. We still need two more eigenvectors. And finally, we encounter this problem because in the past, every time when we find the eigenvalues, I can also find the associated eigenvectors. Even the eigenvalues are repeated, I can still find another two distinct eigenvectors, right? But so far, I cannot find any other eigenvectors that satisfy this eigenvalue. Okay, only 1, 0, 0. So what should we do? Then in this case, we're going to introduce the generalized eigenvectors. Generalized eigenvector. Okay, we know eigenvectors that satisfy this equation. Ax1 equals lambda 1 x1. And then we know A minus lambda I times x1 is 0 vector. And we can find the characteristic equations. Okay. Now I want to find the second eigenvector. We say A x2 equals lambda 2 x2 plus x1. Then this I can get A minus lambda 2, here lambda 1, x2, that's equal to x1. Rather than 0, that's x1. And from both sides, I times A minus lambda 2 I again. So here I times this same thing. I have A minus lambda 2 I squared. In this case, times x2 will be a 0 vector. Okay. Now, for the third one, lambda 3 x3. Now I plus x2, not just x1. In this case, A minus lambda 3 I x3 equals x2. And again, you times A minus lambda 3 I, and also here A times A minus lambda I. Then you get A minus lambda 3 I cube x3 equals 0. Equals 0 vector. Okay, so now I generated two more eigenvectors, x2 and x3. Then I have the P vector, the P matrix formed by those eigenvectors. Then A times P will be matrix A times x1, x2, and x3. So it should be A x1, A x2, A x3. What is AX1? Lambda 1 x1. A times x2. Lambda 2 x2 plus x1. A times x3. Lambda 3 x3 plus x2. This is x1, x2, x3 times lambda 1, lambda 2, lambda 3. Here's O0. But now I have x1 and x2. So here I have 1, 1 instead of all zeros. So this is not a diagonal matrix. But we give this matrix the name Jordan block. Okay. And in this case, you can see A equals P J P inverse, or the Jordan block J is P inverse A P. Then next week, based on this Jordan block, we can express the exponential matrix if you have not sufficient eigenvectors. Or we can say that if you have repeated eigenvalues and not enough eigenvectors, then you need to use this Jordan block to find or to write the exponential matrix. Okay, now let's see this example. X prime equals AX, and I have an A. You can find, this is 3 by 3 matrix. So you can find 3 eigenvalues. The first one is lambda 1. The first eigenvalue is -1. And their associated eigenvector is 1, -2, 0. And the eigenvector, the other two eigenvectors, they are repeated. They are all 3. And you can only find the eigenvector 0, 1, -1. And you cannot find another one. So we need one more. So need one more eigenvector. So if we need one more, A x2 or x3 equals lambda 3 x3 plus x2. So you get A minus lambda 3 I x3 equals x2. Use this equation to find your eigenvector. Okay. Okay. Use this one. You can either write to this square times x3 equals a 0 vector, but I strongly suggest that you use this equation to find your eigenvector. Okay, so in this case, we have 4x1 plus 4x2 because lambda is 3, so 7 minus 3, that'll be 4, plus 4x3 equals 0. Second row, minus 6x1 minus 4 minus 3 minus 7x2 minus 7x3 equals 1. Last row. So now we have this equation. All right, for this equation, we can find x1, x2, and x3. And because how do you find these three variables, x1, x2, and x3? First, we can just, for convenience, we can let x1 equals 1. Once x1 equals 1, for the first row, we get x2 plus x3 equals minus 1. Right. And then we still have two variables. So we can let, suppose that x2 equals c, a constant c. Then I can express x3 as 1 minus c. So for this one, it is based on your x1 and your x3. Well, so if you write it on x1, x2, and x3, overall, x1 is 1, x2 is c, and x3 is minus 1 minus c. Okay, and then we know that we found this eigenvector here. So this is your extended eigenvector, or this one more eigenvector here. Once I have x2 and x3, and also this is my x1, I have the three eigenvectors, then I can form the matrix P minus 1, 1 minus 2, 0, that is x1 here. And then for x2, 0, 1, minus 1, x3, 1, 0, minus 1. Well, don't be confused about these notations with this vector, okay? Those are the just elements. You can put 4a plus 4b plus 4c equals 0, okay? And this is the vector. This is nothing related to these symbols x1, x2, x3. Okay? Maybe next time I will change that to like A, B, C. Try to find A, B, C. This is your matrix P, and since we have a repeated eigenvalues and we need a generalized eigenvectors. So instead of having the diagonal matrix, we have a Jordan block. That is, you still put the eigenvalues, but since these two are repeated and they cannot find their independent eigenvectors, so I know that above this element, I'll get 1 here. This is still 0. That means this vector is a generalized eigenvector. Okay, they are repeated. If you have a repeated eigenvalues and you still can find the different or independent eigenvectors, then here should be 0. But if you cannot find that, we need to use our generalized eigenvectors. Then using this method of generalized eigenvectors, then I need to put 1 here. Okay, 1, that means this. Okay, so every time if you see the matrix, you can immediately tell people how many repeated eigenvalues you have and how many generalized eigenvectors you have. For example, let's show 1 0 0 0 0 0 0 2 0 0 0 0 2. For this matrix, how many generalized eigenvectors do you have? 2, right? Because this is an eigenvalue. Eigenvalue, I have a repeated eigenvalue. Then I check here. I have a 1. So for this repeated eigenvalues, I cannot find 2 independent eigenvectors. Then I need to use a generalized eigenvector. Here, I also have a repeated eigenvalues, and I see here I have a 1. So this is the generalized eigenvectors. If I have 0 here, then that means I have a repeated eigenvalues, but I can't find the distinct eigenvectors. Okay. Because in the past, you see that once you had the repeated eigenvalues, you still can find 2 associated distinct eigenvectors, right? If not, then you need to use generalized eigenvectors. Then here, you definitely need to put 1. Okay. How about here? I have a 0, 2, 2. How about in this case? I have a repeated eigenvalues. 4 repeated eigenvalues. I should have 4 distinct eigenvectors, right? And apparently this, I have a 0 on top. So for this case, I can find 2 independent eigenvectors. But the other 2, I cannot. So I need to use the generalized eigenvectors. Okay, so in this case, I have a 2 generalized eigenvectors. If I have a 0 here, that means for these 4 repeated eigenvalues, I can find 3 associated eigenvectors, but I still need 1 more. So here, that's 1 more. Okay? All right, so back to here. With the Jordan block, we also know I can express the matrix A as P, J, P inverse. Okay, so now I want to find x prime equals AX. What is the answer of X? Here we can also do another method, changing variables. That X equals P Z, which is P times Z1, Z2, and Z3. Then bring it back to the differential equation. X prime equals AX. So I have a P Z prime equals AX. A, that's P J P inverse X. So for this Z, that'll be, here I cancel out. So Z prime will be J Jordan block times Z. So Z1 prime, Z2 prime, Z3 prime. -1, 0, 0, 0, 3. Because Jordan block, you should know how to write this. I have repeated eigenvalues, but I couldn't find the associated two eigenvectors. Then I need to use the generalized, I need to apply the generalized eigenvector. So here I have a 1. And Z1, Z2, and Z3. You can also observe this equation. I decoupled the variables. So Z1 prime just individually have minus Z1. Then you can find Z1 right away. Same thing applies to Z3. So Z1 prime equals minus Z1. Z2 prime equals 3Z2 plus Z3. And Z3 prime equals 3Z3. Then you have Z1 equals C1 e to the minus t. Z2, C2 e to the 3t plus C3 t times e to the 3t. And Z3 will be C3 e to the 3t. That is the answer for Z. Then we need to back to X. X is P times Z. What is your P? 1, 1 minus 2, 0, 0, 1 minus 1, 1, 0 minus 1. And your Z, C1 e to the minus t, C2 e to the 3t, C2, C3 t e to the 3t, and C3 e to the 3t. You can also write it down as C1, 1 minus 2, 0, using columns. Here I have e to the minus t, C2, 0, 1 minus 1, e to the 3t, and C3 overall e to the minus t, minus 2 e to the minus t, 0, 0 e to the 3t, minus e to the 3t, e to the 3t, t times e to the 3t, and minus t minus 1 e to the 3t times C1, C2, C3. So many ways to express your answer. Any questions for this? You mean this one? Well, here. A minus lambda 3i. We know lambda 3 is 3, right? So that's why 7 minus 3, 3, that'll be 4. 4, 4, 4 equals 0. Minus 6, minus 4, minus 7, minus 6, and minus 4, minus 3 will be minus 7. That'll be 1. Okay. Again, that this x1, x2, x3 is a variable. Okay, it is not this vector. Okay, totally not related to this vector. I can put this as A, B, or C. We just try to find this equation. Okay, or I should put like x11, x21, x31. Alright, if you don't have any question, x prime equals ax. So suppose we know that the answer should be a constant times e to the ax, at, right? So in this case, it looks like my answer, this should be e to the at. So for this part, very important that we change the variables to find the answer, but this matrix may not be e to the at. So that's why I said that in the beginning that we can use this method to find the answer. Okay, changing variables, and we still can find the answer, but this is not e to the at, may not be e to the at. Then you may ask that how can I find the e to the at, the exponential matrix form? Especially if I have a repeated eigenvalues, but I cannot find enough eigenvectors, associated eigenvectors, then I need to use the generalized eigenvectors. Then how can I express e to the at? Here. Suppose A is 4x4 matrix. I have repeated eigenvalues, and I only have one associated eigenvector, C1. So I only have one associated eigenvectors. So I know that my Jordan block, for repeated, I can only find one associated eigenvectors. So the rest will be the generalized eigenvectors. So I will put 1 here. Okay. Now my goal is to find the exponential matrix. Okay. How do I find e to the at? So my matrix A can be written as here. How about a square? If I have a square, that means p j p inverse times p j p inverse. So they can cancel it. So they have p j square p inverse. This is Jordan block square. Okay, you times this again, then you get this one. If we do the cube, then there will be j cube. J cube is here. Can you observe something from these 3 examples? A square and a cube. Actually, j square and j cube. Jordan block, that you have to find it, right? Once you found it, the Jordan block, it looks like you can write j square right away, j cube, or even you can predict j to the 4th. Okay, right, C. Because I have a square, so lambda, I have lambda square, obviously. But right above the main diagonal elements, here I have 2 lambda. And then later on, I have a 1. It looks like this part, I can take the derivative of the main diagonal elements. Lambda square, now the next level, I take the derivative, it'll be 2 lambda. Okay, and how about 1? I take the derivative again, and it should be 2, right? Then I divide by 2 factorial. This one, lambda cube, the next one you take the derivative, so 3 lambda square. Take the derivative, 3 lambda square, take the derivative. I should get 6 lambda, but I need to divide 2 factorial, so I get 3 lambda. And then I take the derivative again. Then you'll get 1. It should be 3, but you divide by 3. Then you get 1. Okay? So this is just the Jordan block. But now, if I have a function for different kind of function, then what is the f of a matrix? Let's see why you have this pattern. Okay, so for the function, I know the function of x, one variable, but what is the function of a matrix? Suppose my function is a polynomial, then I just changed it to the matrix. So f of a matrix, it should be a naught with identity matrix, and here x, I just changed it to matrix a squared, a cubed, and so on. And then I change a to I can find the eigenvectors and also eigenvalues. I change that to express it as a p, j, p inverse. So overall, you can take p outside and p inverse outside. In the middle, this is like a series expansion. Okay, for this series expansion, that's the form. The first, f of lambda. The second one, I take the derivative. Next one, I take the derivatives again, but divide by 2 factorial. Next one, I will divide by 3 factorials. And then later on, you have 4 factorials, 5 factorials, and this is the final form. If I have a Jordan block, then what is the function of a Jordan block? There we go. So that means if I have a Jordan block n by n, then e to the jt, I can take the exponential to the lambda t outside, and here's the rest. Okay, let's just see this example, and you will know how to find the exponential matrix. So first, for this matrix, please give me the eigenvalues and also the eigenvectors. What are the eigenvalues and eigenvectors? I have a repeated eigenvalues actually, -2, -2. So first, let's see what is the eigenvector. To find the eigenvector, -6, 9, -4, and 6 times k1, k2 is 0. So my first eigenvector, 3k1 plus 2k2 equals 0. How do you choose your eigenvector? Well, I can choose -2 and 3. Can you find another eigenvector here? No, right, except 0, 0, but 0, 0 cannot be the eigenvector. So I only have one equation, and then I cannot find any other eigenvector. So I need a generalized eigenvector. So for generalized eigenvector, -6, 9, -4, 6 times your x2. This should be your x1. And then you can find your x2 is 1/3 0. And here very important. If you calculate minus 6, 9, minus 4, 6, and you times that same matrix again, that equals times x2 equals 0. It is also okay, but it will be really hard to choose the correct x2 because you have if you times this together, you have 0, 0, 0, minus 72, x2 equals 0 vector. And it is really hard to choose the correct x2. So in this case, I have a matrix P. Minus 2, 3, 1/3, 0. And your P inverse 0, 3, 1/3, 2. Then your matrix A, P, J, P inverse. It should be P. What is your Jordan block? This is repeated, so here I have a 1. Remember that when I put 1, that means they are repeated, and I cannot find their associated eigenvectors. If you put 0, that means you have 2 repeated eigenvalues, and you can also find 2 different eigenvectors. 2 different independent eigenvectors. If you cannot, then you need to use Jordan block. That's why we put 1. So in this case, we can have e to the jt e to the minus 2t 0 e to the minus 2t here's minus 2, so e to the jt becomes e to the main diagonal elements. It will become e to the minus 2t. For this part, you don't need to care about this. For this part, take the derivatives. If you take the derivatives of e to the minus 2t, you get t times e to the minus 2t. This part, we always need to keep this the original form e to the minus 2t. The first part you put the t, and the second part, if we have a bigger matrix, then you have 1 over 2 factorial t times t squared, just like this one. Okay. Once you have the exponential matrix of e to the jt, then you can get the exponential matrix of e to the at. And then this is your exponential matrix 4.